So we're going to evaluate this series from a Hong Kong math competition. 17 over 75 times 76 plus 17 times 18 over 75 times 76 times 77 plus 17, 18, 19 over 75, 76, 77, 78, and so on to infinity. And this series is quite the beast. It is going to be absolutely amazing to evaluate this. So to start off, let's call this sum S. And what I see when I look at this problem is numbers being multiplied together where each number is one more than the last. 75, 76, 77, 78, 17, 18, 19, same thing. And that reminds me of factorials. And I like factorials because they're usually easier to deal with. But these aren't factorials right now because they don't go all the way down to 1. Is there a way that we could make them go down to 1? Well, what happens if we take the sum and multiply it by 16 factorial? Well, what happens on the top here? Right now we have 17. 16 factorial is 1 times 2 times 3 up to 16. If we multiply by 17, that gives us 17 factorial. And then the next term will be 1, 2, 3 up to 16 times 17 times 18. Well, that would be 18 factorial. And then the next one would be 19 factorial, and so on. So that's nice. Can we do something similar to the bottom? Well, yeah. If we divide by 74 factorial, then on the bottom, for the first one, we get 1 up to 74 times 75, 76 will give us 76 factorial. The next one, we go up to 76 times 77 is 77 factorial, then 78 factorial, and so on, just like this. And now we can write this in terms of a summation. So this is going to be equal to the sum from k equals 17 to infinity of k factorial on the top, and then k plus something factorial on the bottom, because we know it's going up by 1 each time. And that something is going to be 59, because 17 plus 59 is going to give us 76. And now what we notice is there's actually going to be some cancellation between the top and the bottom. If we think about k plus 59 factorial, well, that's going to be equal to k factorial times k plus 1 times k plus 2 times k plus 3, all the way up to k plus 59. So in fact, this sum is just equal to 1 over k plus 1 times k plus 2, all the way up to k plus 59. So what do we do from here? Well, to start, I'm going to consider a simpler series, the sum from n equals 1 to infinity of 1 over n times n plus 1. What you would do to evaluate this normally is you would split the denominator up using partial fraction decomposition. And then the result of that would be 1 over n minus 1 over n plus 1. That way, if you evaluated this sum from n equals 1 to infinity, you get 1 over 1 minus 1 over 2, then plus 1 over 2 minus 1 over 3, plus 1 over 3 minus 1 over 4, and so on. And what you would get is minus 1 over 2 plus 1 over 2 cancels, the 3's cancel, the 4 cancels, everything cancels except for the first. And this is called a telescoping sum. Well, in this case, we only have 2 terms here, and it telescopes. Here we have 59 in our original sum. Are we going to use partial fractions on this one? We're going to use partial fractions on this one. So let's look at the inside of this sum here. 1 over k plus 1 times k plus 2 times k plus 3, all the way up to k plus 59. And this is going to be equal to, all these terms are linear. So let's call the constants that they're multiplied by c sub whatever it is. So c1 over k plus 1 plus c2 over k plus 2, and so on c59 over k plus 59. And before we figure out what these constants equal, I want to observe something about what we have right here. What happens if we multiply by the entire denominator? Well, on the left side, we'll just get 1. On the other side, let's just look at what happens to the k to the power of 58th term. In each of these terms on the right here, in order to get k to the 58th, because one of these 59 things is going to cancel in every case, all of the other ones are going to have to take the k to the 58th. And then that leaves you only with the constant multiple. So for this one, we get c1 times k to the 58th. For the next one, we get c2 times k to the 58th. And so on, c59 times k to the 58th. And then plus whatever else is over there. But notice on the left, how many k to the 58ths do we have? Well, we have 0. There's no k to the 58th on the left. which means this thing in here has to be equal to 0 in order for this equation to be true. So in fact, and I'm going to write this over here because it's going to be important later, the sum from k equals 0 to 59 of c sub k is going to be equal to 0. That has to be true in order for our partial fractions to work. So now it's time to figure out exactly what each of these constants is equal to. And because all the terms are linear, that means we can use the cover-up method. So let's see what happens here. First of all, for the k plus 1 term, in order for k plus 1 to equal 0, we want k to equal negative 1. So if we go over here to the left side and cover up k plus 1, and then we plug in negative 1, well, we're going to get negative 1 plus 2 is 1, negative 1 plus 3 is 2, and then so on up to negative 1 plus 59 is 58. So we'll get 1 over 1 times 2 times 3 times up to 58 times 1 over k plus 1. Then we'll get plus, what about c2? Well, in order for k plus 2 to equal 0, we want k to equal negative 2. So you go over here, cover up k plus 2, and then we plug in negative 2 plus 1 is negative 1. So I'll put that first. And then we have times negative 2 plus 3 is 1. The next one would be negative 2 plus 4 is 2. And then 3 up to negative 2 plus 59 is 57. So then we have 1 over that times 1 over k plus 2. And then I'm going to skip forward to the over k plus 59 term. So for that, we want k to equal negative 59. So you go over here, cover up k plus 59. Then we have negative 59 plus 1 is negative 58. The next one would be negative 57, then negative 56, and all the way down to negative 59 plus 58, which would be negative 1. And then we multiply that by 1 over k plus 59. So let's see if we can notice a pattern in the constants that we have right here. To start out, for this 1 over k plus 1, we notice that we have a 58 factorial. So we can write that right here, 1 over k plus 1, because we have 1 times 2 times 3 all the way up to 58. Next, on this one, first of all, we have a negative 1. So I'll write the negative 1 on the top here. Then we have just a 1 by itself. That's going to be a 1 factorial. Then we have 1 times 2 times 3 up to 57 is 57 factorial. If we think about what the k plus 3 term would have been, we go over here, cover up k plus 3, and plug in negative 3. Well, that would be negative 3 plus 1 is negative 2, and then negative 3 plus 2 is negative 1. So the k plus 3 term over here would actually be divided by, well, we have negative 2 times negative 1. That'll be a negative 1 squared over 2 factorial. And then if we plug in negative 3 up here, we get 59 minus 3 is 56 factorial. Now we notice a pattern of 2 factorials in the denominator. If we look at this first term again, this k plus 1 term, we can think about having a 0 factorial, because that's just equal to 1, which corresponds to not multiplying anything over here. And then we also don't have any negatives, so we can write negative 1 to the 0. Now, can we notice a pattern here? If we think about this as negative 1 to the first, notice that the power of negative 1 goes up by 1 every time. And in addition, these factorials, the first factorial goes up by 1. So it goes 0, 1, 2, 3, and so on. And then the second factorial goes down, 58, 57, 56, all the way down. And in fact, if we look at the final term here, we have plus 1 over, notice we have negative 1 to the power of 58, because we have 58 negative things multiplied in the bottom. And then on the bottom, we're going to have 58 factorial, because we have 58, 57, 56 down to 1, times 0 factorial, because there's nothing multiplied here, times 1 over k plus 59. And this follows the exact same pattern. Let's think about a general form of these constants if we want to have c sub m. Well, first of all, notice, for example, for the k plus 3 term, we have a power of 2 on the top. So that's corresponding to 3 minus 1. So we can think about m minus 1. Similarly, for the k plus 2, we have 2 minus 1 is 1. 59 minus 1 is 58, and so on. And notice that there's the same power in the denominator in these factorials here as there is in the negative 1 power, which means we're also going to have an m minus 1 factorial being multiplied. Now if we look at the other factorial, for example, k plus 59, we get 0 factorial. Well, 0 is 59 minus 59. For k plus 2, we get 57. 57 is 59 minus 2. So in general, we're going to have 59 minus m factorial as the last thing being multiplied. So this is the general form for our constants, and that means that we can write this whole giant fraction right here in terms of a sum. So I've cleared the board to give us more space, and now we can write this original infinite sum in an expanded form by writing this entire fraction as a sum itself. The sum from m equals 1 to 59 of c sub m, this thing right here, times 1 over k plus m. So for example, k plus 2 is going to have c sub 2 multiplied by it. And we have 1, 2, 3, 4, all the way up to 59 on the top right here. So I've again cleared the board a little bit and written this double summation right up here. Know that it's equal to 16 factorial over 74 factorial times s. Now before we try to do any tricks on this sum right here, let's see if we can write out a few of the terms and get a feel for what we have right here. So this is going to be equal to, starting with k equals 17, we'll have c1 over 17 plus 1 is 18, plus c2 over 17 plus 2 is 19, then c3 over 20, all the way up to c59 over, and then 17 plus 59 is 76. Then, when we have k equals 18, we'll have c1 over 18 plus 1 is 19, then c2 over 20, and so on up to c58 over 58 plus 18 is 76, plus c59 over 77. And then the next one will be c1 over, this time k is 19, so you get c1 over 20, plus blah, 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 plus c57 over 76, plus c58 over 77, plus c59 over 78. And this goes on to infinity. So let's think a little bit about what happens here. Consider the denominator 1 over 76. What constants get multiplied by 1 over 76 in this giant sum? Well, we see c59 gets multiplied by 1 over 76 here. c58 does as well. c57 does. In the next term, c56 would get multiplied by it, then c55 and c54 and so on. Because these denominators keep increasing, eventually even c1 is going to get multiplied by 1 over 76, which means every single constant is going to get multiplied by 1 over 76 and added together. Added together to equal exactly 0, which means the denominator of 76, we can completely ignore. It telescopes out. What about 77? Well, c59 gets 1 over 77. c58 does. Next would be c57, c56. All the constants are going to get the denominator of 77. That adds to 0 as well. 78 adds to 0 as well. 79, 80, everything greater than or equal to 76 is out. It all gets canceled to 0 because of this fact that the constants add to 0. This is the biggest telescoping sum you've ever seen. Now, what we want to consider is what happens to the denominators that do not get added up to 0. Let's consider, for example, the denominator of 18. C1 has 1 over 18. C2 never does. It starts at 19 and then keeps going up. So for 18, we only get C1. For 19, we get C2 and C1. For 20, we get C3, C2, and C1. So every time, as these denominators increase by 1, we get an additional constant, all the way up to 76 when all of the constants are included, and then it just adds to 0. Let's see if we can find a general formula for which constants get multiplied by a particular denominator. Say we have the denominator w plus 18, since we're starting at 18 here. Let's see what it gets mapped to. Well, for example, 20 is 2 plus 18, and it gets mapped to C1, C2, and all the way up to C3. Well, 20 is 2 plus 18. 3 is going to be 2 plus 1. So it seems like it gets mapped to CW plus 1. If we look at 19, 19 is 1 plus 18. So it gets C1, C2, all the way up to C1 plus 1, which is C2. So that's right. Same applies for 18. C0 plus 1 is C1. So that's correct. In general, if we want to write this sum as our telescoping sum in terms of the denominators, W is going to go from 0 for 1 over 18, all the way up to whatever makes W plus 18 equal to 75. and that's going to be 57, because 57 plus 18 gives us 75. Then we have 1 over w plus 18 is this denominator constant here, and then that gets multiplied by the sum from m equals 1 to w plus 1 of c sub m. And notice now that we've written our infinite sum as a finite double sum, which means we are indeed making progress towards solving this problem. So I've given us some more space, and we are going to erase our original form of the sum and write it in the new form, but we're also going to plug in the value of c sub m. So this is equal to the sum from w equals 0 to 57 of 1 over w plus 18 times the sum from m equals 1 to w plus 1, and then c sub m is negative 1 to the m minus 1 over 59 minus m factorial times m minus 1 factorial. Now, in order to make this a little bit easier to deal with, I noticed that we have a lot of m minus 1 flying around everywhere, and that's kind of annoying. So let's make a change of variables here. Say we let k equal m minus 1, and we're just going to shift the whole sum down 1. So that gives us that we have the sum from w equals 0 to 57 of 1 over w plus 18 times the sum. Well, if m equals 1, then k is 1 minus 1, which is just 0. And then w plus 1 minus 1 is w. Then we have negative 1 to the k over. If we think about this, if k equals m minus 1, m equals k plus 1. So if we plug that in here, we get 59 minus k and then minus another 1. So we'll have 58 minus k factorial and then k factorial. So now let's take a look at this sum that we have right here on the inside. What we notice is that there are 2 factorials on the bottom. And the one other time that I remember having 2 factorials on the bottom is when we have the case of x choose y, which is equal to x factorial over y factorial times x minus y factorial. This is the other case where we see 2 factorials. And it also looks very similar because we have things being subtracted here in both cases. But right here, we're missing a factorial on the top that we want to have in order to use this x choose y notation. Let's think about what this 58 minus k factorial times k factorial looks like in terms of this. Well, if we let y equal k, then we have something choose k is going to be equal to something factorial over k factorial times something minus k factorial. What is that something? Well, we know it's got to be 58 for this to work. So 58 minus k factorial, and that makes this top 58, and we have 58 choose k. So this is the form that we want. Notice we're missing a 58 factorial, but that's a constant. So if we think about our sum right here, s, 16 factorial over 74 factorial s, what if we just multiply both sides by 58 factorial? Then we get another constant over here for s. We can cancel that out later. But now we have 58 factorial over here. And we can write this part as 58 choose k. So we get that this sum is equal to the sum from w equals 0 to 57 of 1 over w plus 18 times the sum from k equals 0 to w of negative 1 to the k times 58 choose k. And now I've already derived an identity that has to do with this sum right here. You can watch the link in the description for the proof. This sum right here, the sum from k equals 0 to w of negative 1 to the k times n choose k, is equal to negative 1 to the w times n minus 1 choose w. And we can immediately plug that in to turn our double sum into nothing other than a single sum. So that has significantly simplified our calculation here. And we know this sum is equal to negative 1 to the w times 58 minus 1 is 57, choose w. And all we have to do now is evaluate this single sum. The question is, how do we do that? Well, first of all, let's consider what would happen if we didn't have this w plus 18. This looks a lot like the binomial expansion. So for example, if we have 1 plus x to the power of n, that equals the sum from k equals 0 to n of x to the k times n choose k. So if we plugged in 57, well, then we would have 57 on top here, and then 57 choose k. So that all looks good. But we're missing this 1 over w plus 18. So we need to have some way to add that into our summation. And here's what we're going to do in order to do that. If I just told you that we had a 1 over w plus 1 on the bottom, well, one thing you might think to do is integrate this on both sides. Because by the power rule, the integral of x to the k would be x to the k plus 1 over k plus 1. And that would give us this denominator that we want. But we don't have w plus 1, we have w plus 18. So if we're looking at this sum over here in terms of w, how can we make this a w plus 18 when we integrate? In order to do that, what if we multiply by x to the 17 on both sides? Well, then what we're going to get on the other side, if we multiply by x to the 17, we can bring that into the sum. And we'll have x to the w plus 17 on the inside just like that. Plugging in 57 for our power here, so we get 1 plus x to the 57, and then 57 choose w. When we integrate this on both sides, we will get this exact sum here, and then we just have to plug in -1. Now we could do the indefinite integral, but I don't really want to do the indefinite integral of 1 plus x to the 57 times x to the 17. That does not seem very nice. So let's think of a way to do a definite integral that lets us plug in bounds directly. If we want to do that, we can think about taking the integral. One bound has to be -1 because we want to plug in -1. The other bound I'm going to set to 0 because that way when we evaluate this, we'll have x to the w plus 18 or 0 to the w plus 18, which just goes away because 0 to the anything positive is 0. So let's take the integral from 0 to -1 on both sides with respect to x. And if we figure out what that's equal to, that is going to be our sum. So to start off, let's write this to the outside. I'm going to do a substitution of u equals 1 plus x, which means du equals dx. So that'll give us the integral. 1 plus 0 is 1, 1 plus -1 is 0. And then we're going to have u to the 57, and then x is going to be u minus 1. So we get u minus 1 to the 17 du. Now let's consider this u minus 1 to the 17. I'm going to write it as -1 to the 17 times 1 minus u to the 17. So I've just taken a -1 out and distributed the powers. Notice -1 to the 17 is just equal to -1 because it's an odd power up there. And what that means is we can use this remaining -1 to flip the bounds around. So this integral is going to equal the integral from 0 to 1 of u to the 57 times 1 minus u to the 17. So we've used this negative to switch 1 to 0 into 0 to 1. And then we have du. Now the last thing I'm going to do before we evaluate this is write 57 as 58 minus 1 and 17 as 18 minus 1. And what this does is it actually puts the integral in the form of something called the beta function of 58 and 18. And I've already done a video on this. You can find the proof in the description that this is actually going to be equal to 58 minus 1 factorial times 18 minus 1 factorial over 58 plus 18 minus 1 factorial, just like that. So we have evaluated this integral very easily. Again, link in the description. And this is all we have left for our sum. We've completely finished. All we have to do now is go back to this equation that we have right here and multiply out this term next to the s to figure out exactly what our sum equals. So I've cleared the board a little bit here, and like I said before, this factorial thing right here is exactly equal to that last sum that we were trying to figure out. So this 16 factorial, 58 factorial over 74 factorial s is equal to 58 minus 1 is 57 factorial, 18 minus 1 is 17 factorial, and then 58 plus 18 minus 1 is going to give us 75 factorial. Now we multiply by this thing over here on both sides. So s is going to be equal to, first of all, if we multiply by 74 factorial, 74 factorial over 75 factorial is going to be 1 over 75. 17 factorial over 16 factorial is going to leave us with a 17 on the top. And then 57 factorial over 58 factorial is going to give us another 58 in the denominator, just like that. So this is the final version of our sum. And one last thing you can do just to make it very nice is to write it as 17 times 75 and 75 minus 17 in the denominator, just like that. So that is the final result of our sum. And the method for evaluating this is just so great. I love doing these kinds of sums because there are so many different things that it brings in with integrals and the binomial coefficients and all that kind of stuff is just great. So if you have any friends that like math and like doing awesome sums like this, show this video to them as well, and subscribe if you want to see more cool stuff like this. Now, another math YouTuber named Famatica also found a solution to this sum right here, but we came up with our solutions completely independently. So he's going to use a different method to get to the answer. And if you want to see more ways to evaluate this sum and more interesting tricks like the ones I showed here, you can check out his video as well. The link will be in the description. And I hope you enjoyed this beast of a sum.